Imagine for a moment a single event so powerful that it unleashes more energy in mere seconds than our Sun will produce over its entire 10 billion-year lifespan. Picture a flash of light brighter than a billion galaxies, erupting from the depths of space, visible halfway across the observable universe. This isn't science fiction. This is the staggering reality of the most energetic explosions our cosmos has to offer. Across the vast, silent expanse of space, titanic forces collide, stars detonate, and black holes awaken in cataclysmic displays that defy comprehension. Today, we're diving into the heart of these cosmic firestorms, uncovering the secrets behind the universe's most violent and spectacular outbursts. Think about the sheer scale of these events. A gamma-ray burst, for instance, can release more energy in 10 seconds than our Sun will emit over its entire existence. These are not just distant curiosities. They are the universe's way of reminding us of its raw, unfathomable power. From hypernovas to magnetar flares, each explosion tells a story of extreme physics, where matter is stretched, twisted, and annihilated under conditions more extreme than anything we could recreate on Earth. These aren't just flashes in the dark, they're the birth cries of black holes, the death throes of massive stars, and the unimaginable turbulence of space-time itself. So what makes these explosions so uniquely violent? How do they shape the cosmos around them, seeding galaxies with the elements needed for life? And what would happen if one occurred dangerously close to our own corner of the universe? Over the course of this journey, we'll unravel 30 astonishing facts about these cosmic spectacles, each more mind-bending than the last. You'll discover how scientists detect these bursts across billions of light years, why some of them could threaten life on Earth, and how they've helped rewrite our understanding of physics itself. This is the story of the universe's most extreme fireworks, and by the end, you'll never look at the night sky the same way again. So buckle up, we're about to venture into the heart of the cosmos's most energetic explosions. Gamma-ray bursts are the universe's ultimate light show brief, blinding flashes so intense they momentarily outshine everything else in the cosmos. Imagine a single explosion so powerful it can emit more energy in 10 seconds than our entire Milky Way galaxy does in a century. These bursts, often abbreviated as GRBs, were first detected by accident in the late 1960s, when American satellites designed to monitor nuclear tests during the Cold War picked up mysterious bursts of gamma rays coming not from Earth but from deep space. At first, scientists were baffled. Some theories even suggested they might be signals from advanced alien civilizations. But as more data poured in, the truth proved even wilder. These were natural cosmic catastrophes on an unimaginable scale. The shortest GRBs last just milliseconds to a couple of seconds, while the longest can stretch for several minutes. But don't let their brief duration fool you. These blasts are thought to be the birth announcements of black holes, created when massive stars collapse under their own gravity or when two hyperdense objects like neutron stars violently collide. The energy released in these events is so concentrated that if you were to witness one up close, though you wouldn't survive the experience, the sheer brightness would outshine the noonday sun by a factor of millions. Even from billions of light years away, modern telescopes can detect their afterglow, a fading echo of light that lingers for days or even weeks across multiple wavelengths. What's truly staggering is how these explosions stack up against the rest of the universe. A single gamma-ray burst can temporarily outshine every star in its host galaxy combined. To put that in perspective, our Sun produces enough energy every second to power human civilization at its current rate for about 500,000 years. And yet, a GRB emits that much energy a billion times over in the blink of an eye. Some of these events are so distant that their light has traveled for more than half the age of the universe before reaching us, carrying secrets about the cosmos in its earliest epochs. And while we've made huge strides in understanding them, GRBs remain one of astronomy's most thrilling enigmas, reminders that the universe still holds mysteries capable of humbling even the sharpest scientific minds. The next time you gaze up at the night sky, remember somewhere in the depths of space, a star might be meeting its end in the most spectacular way possible, unleashing a torrent of energy that could rewrite the rules of physics as we know them. And thanks to the tireless work of astronomers, we're piecing together the story of these cosmic firestorms, one brilliant flash at a time. In October 2022, astronomers witnessed something extraordinary. A gamma-ray burst so brilliant it earned the nickname the BOAT, short for brightest of all time. Officially catalogued as GRB 221009A, this cosmic explosion was so intense it temporarily blinded most gamma-ray detectors in space, despite originating a staggering 2.4 billion light-years away. To grasp just how bright this event was, picture all the stars in the Milky Way combined, then multiply their output by a factor of thousands, and you're still not close. This wasn't just another GRB, it was a once-in-a-10,000-year event, rewriting the playbook on how we understand these cosmic cataclysms. What made the BOAT so special wasn't just its raw power, it was the way its afterglow defied expectations. Normally, the fading light from a gamma-ray burst follows a predictable pattern, dimming steadily over days or weeks, but this one didn't play by the rules. Instead of fading smoothly, its afterglow flickered unpredictably, as if some unseen force kept pouring energy back into the system. Scientists were left scratching their heads, realizing their models couldn't fully explain what they were seeing. Some theorized the explosion might have produced a highly structured jet, narrower and more focused than usual, while others suggested it could have interacted with dense material surrounding the dying star, creating shockwaves that reignited the afterglow. Whatever the cause, the BOAT forced physicists to reconsider long-held assumptions about how these bursts evolve. The implications of this event stretch far beyond just breaking brightness records. By studying the BOAT's unusual behavior, researchers gained new insights into the extreme physics at play during a gamma-ray burst. For instance, the afterglow's flickering hinted at complexities in how energy is transferred within these jets' processes that could help explain how heavy elements like gold and platinum are forged in the universe. There's even speculation that a similar burst occurring closer to our galaxy could pose a real threat to Earth's ozone layer, reminding us that these distant fireworks aren't just awe-inspiring, they're a reminder of the universe's capacity for destruction on an unimaginable scale. Yet, despite the mysteries it left behind, the BOAT also showcased how far astronomy has come. Just a few decades ago, we might have missed an event like this entirely. Today, an army of space telescopes and ground-based observatories stands ready to catch every fleeting detail, turning what would once have been a cosmic curiosity into a treasure trove of scientific discovery. And as astronomers continue to sift through the data, one thing is clear: the universe still has plenty of surprises up its sleeve, waiting for the next brilliant flash to light the way. To understand the sheer destructive power of a hypernova, let's start with something familiar: the humble supernova. A typical supernova marks the explosive death of a massive star, blasting its outer layers into space with enough force to briefly outshine its entire galaxy. Imagine our sun suddenly exploding with the energy of 100 billion stars. That's the scale we're talking about, but even that pales in comparison to a hypernova, which cranks the devastation up to unimaginable levels. Think of it like this: if a supernova is a stick of dynamite, a hypernova is an entire nuclear arsenal detonating at once. The key difference lies in the engine behind these explosions. While a regular supernova occurs when a massive star collapses and rebounds in a fiery explosion, often leaving behind a dense neutron star, a hypernova happens when the star is so massive, think 20 to 40 times heavier than our sun, that its core doesn't just collapse into a neutron star. Instead, it keeps going, plunging straight into the abyss to form a black hole. This catastrophic collapse isn't just a one-and-done explosion. It channels mind-bending amounts of energy into twin jets of ultra-relativistic particles, screaming outward at nearly the speed of light. These jets are so focused and energetic that if one happens to be pointed directly at Earth, we detect it as a gamma ray burst, the universe's most powerful flashbulb. Here's where the numbers get truly staggering. A typical supernova releases about 10 to the 44 joules of energy, enough to outshine a galaxy for weeks. But a hypernova, multiply that by 50 or even 100, unleashing up to 10 to the 46 joules in mere seconds. To put that into perspective, our Sun will radiate roughly 10 to the 44 joules over its entire 10 billion-year lifespan. That means a hypernova, in the blink of an eye, can outshine the Sun's total lifetime output by a factor of 100. It's the difference between a firecracker and a thermonuclear bomb. What makes hypernovas even more fascinating is their role as cosmic alchemists. These explosions are so violent they forge elements far heavier than iron, gold, platinum, uranium, flinging them into the cosmos like celestial confetti. Without hypernovas, the universe would lack the building blocks for planets, life, and even the device you're using to watch this right now. And while we've never witnessed one close enough to feel its effects, astronomers suspect a hypernova within a few thousand light-years could strip Earth's ozone layer, triggering mass extinctions. So next time you hear about a supernova, remember, somewhere out there, a hypernova is rewriting the rules, proving that even in death, the most massive stars go out not with a whimper, but with a universe-shaking bang. If a hypernova is the universe's ultimate demolition derby, then a kilonova is its most spectacular jewelry store, where cosmic collisions forge gold, platinum, and other precious metals in quantities that would make even a dragon's hoard look meager. Picture two city-sized remnants of dead stars, each so dense that a single teaspoon of their material would weigh as much as Mount Everest, hurtling toward each other at nearly a third the speed of light. When they collide, the impact doesn't just shake the fabric of space, it sends literal ripples across the universe and sprays out enough gold to gild every planet in our solar system 1,000 times over. This is the mind-bending reality of a kilonova, one of nature's most extravagant displays of alchemy. The historic event that put kilonovas on the map happened on August 17, 2017. When gravitational wave detectors LIGO and Virgo picked up vibrations in spacetime labeled GW170817. For the first time in history, astronomers didn't just hear the crash, they saw it. Telescopes around the world swiveled toward a faint galaxy 130 million light-years away, capturing the kilonova's afterglow in unprecedented detail. The data revealed something extraordinary. In the fiery aftermath of the collision, a torrent of neutrons bombarded lighter elements, transforming them into heavy metals like gold, platinum, and uranium. Scientists estimate this single event produced somewhere between 3 and 10 Earth masses worth of pure gold, along with other rare elements. To put that in perspective, all the gold ever mined in human history would fit into just 3 Olympic-sized swimming pools. This kilonova made that look like pocket change. But the real magic lies in how these collisions work. When two neutron stars spiral into each other, their immense gravitational forces shred them apart in a matter of milliseconds, creating a swirling maelstrom of ultra-hot debris. The outer layers eject at relativistic speeds, glowing blue from the heat of radioactive decay, while the cores either merge into a new black hole or, if they're just light enough, collapse into an even more massive neutron star. The entire event unfolds in less time than it takes to brew a cup of coffee, yet the energy released is enough to outshine 1,000,000 suns. And because neutron stars are essentially giant atomic nuclei, their collisions act like cosmic particle accelerators, forcing protons and neutrons together under conditions so extreme they form elements that would be impossible to create anywhere else. What makes kilonovas especially thrilling for scientists is their dual signature nature. Unlike gamma-ray bursts or supernovas, these events announce themselves with both gravitational waves and light, offering a multi-messenger window into the universe's most violent processes. The gravitational waves reveal the precise moment of collision, the crescendo of space-time itself bending under the star's immense weight, while the light show that follows unveils the aftermath, painting a picture of how raw energy transforms into tangible matter. It's like watching a car crash in slow motion, then sifting through the debris to find the engine has somehow turned into solid gold. The legacy of GW 170817 goes beyond just confirming where heavy elements come from. It proved that when humanity's tools align, combining gravitational wave astronomy with traditional telescopes, we can decode the universe's most cryptic messages. And as more detectors come online, we're on the brink of discovering dozens, perhaps hundreds of these events, each one offering a fresh chance to unravel how the cosmos turns destruction into creation. So the next time you slip on a gold ring or glance at a platinum watch, remember, you're wearing stardust forged in a cataclysm so violent, it sent shockwaves through the very fabric of reality. Deep within our galaxy, cosmic powerhouses known as magnetars lurk, neutron stars so magnetically charged they could erase your credit card from halfway across the solar system. These stellar remnants pack the mass of a sun into a sphere no wider than Manhattan, spinning furiously while wielding magnetic fields 1,000 trillion times stronger than Earth. To grasp that kind of power, imagine a magnet so intense it could liquefy your atoms from a distance of 600 miles. Yet even these extreme objects have their breaking points. When their crusts crack under unimaginable magnetic stress, the resulting starquakes unleash eruptions of energy that make solar flares look like birthday candles. One such explosion, detected on December 27, 2004, rewrote the rules of what we thought possible. A magnetar named SGR 180620, located 50,000 light-years away in the constellation Sagittarius, let loose a flare so powerful it briefly outshone the full moon in gamma rays, despite being buried deep inside our galaxy's dusty core. The outburst, lasting just a fifth of a second, released more energy than our sun emits in 250,000 years. But here's what's truly mind-bending. That tiny pulse of radiation was strong enough to ionize Earth's upper atmosphere, distorting radio signals worldwide and even temporarily knocking out some satellites. Scientists compared it to a cosmic EMP, proving that magnetars don't just flicker. They scream across the cosmos with enough force to reach into our planet's atmosphere from beyond the galactic suburbs. What causes these apocalyptic tantrums? Picture a neutron star's crust, a crystalline lattice of iron nuclei, packed as tightly as atoms in a diamond, strained beyond endurance by magnetic fields twisting like rubber bands. When the tension finally snaps, the crust fractures, triggering seismic waves that ripple across the star's surface at near-light speeds. These starquakes launch tsunamis of charged particles along the magnetar's magnetic field lines, which then collide and release torrents of X-rays and gamma rays. It's like snapping a giant cosmic whip where the crack is a pulse of radiation visible across interstellar space. The 2004 event wasn't just a record breaker, it was a wake-up call. Had SGR 180620 been 10 times closer, the flare could have stripped our ozone layer, triggering mass extinctions. Yet these cataclysms also serve a purpose. By studying magnetar outbursts, astronomers have discovered that their magnetic fields can twist spacetime itself, creating detectable ripples in the fabric of the universe. Some theorists even suggest these flares might solve long-standing mysteries about fast radio bursts, those enigmatic cosmic signals that have puzzled scientists for years. So while magnetars might seem like distant oddities, their flares remind us that the universe is anything but quiet. In a cosmos where stars can crack like eggshells and magnetism bends the rules of physics, these ultra-dense power stations continue to challenge our understanding of how matter behaves under the most extreme conditions imaginable. And with every starquake they unleash, they offer physicists front row seats to forces so intense they redefine what we thought was possible. At the heart of nearly every massive galaxy, a supermassive black hole feasts on swirling disks of gas and dust, but some of these cosmic monsters don't just consume silently. They spit. When conditions are right, these gravitational behemoths launch twin jets of charged particles at nearly light speed, stretching across millions of light years like celestial blowtorches. These are quasar jets, and they're among the most energetic phenomena in the universe. Picture a flashlight beam so intense you could see it from the edge of the observable universe. That's the raw power we're talking about. The physics behind these jets is as mesmerizing as their appearance. As matter spirals toward a black hole's event horizon, friction and magnetic fields heat it to billions of degrees, turning the accretion disk into a particle accelerator. But not all that material gets swallowed. Some gets funneled along the black hole's spin axis, channeled by magnetic fields into narrow, ultra-focused beams. The result, a pair of relativistic jets punching through space with such force they can plow through entire galaxies, heating intergalactic gas and triggering or stifling star formation in their wake. What makes these jets truly remarkable is their sheer scale. Take the Quasar 3C273, whose jet stretches over 1.5 million light-years, 15 times the diameter of our Milky Way. At that distance, the particles in the jet should have dispersed into nothingness long ago, yet they remain tightly collimated, defying expectations. The secret lies in the jet's structure. They're not just streams of particles, but twisted ropes of magnetic energy that act like cosmic pipelines, keeping the energy focused across mind-boggling distances. And then there's the light show. As these jets slam into intergalactic material, they create shock waves that glow across the electromagnetic spectrum. From radio waves visible to our telescopes up to gamma rays powerful enough to pierce through gas and dust. Some jets even appear to move faster than light, an illusion caused by their near-light-speed trajectories pointing almost directly at us. It's like watching a cosmic lighthouse beam sweep past Earth, each pulse carrying secrets about the black hole that launched it. But perhaps the most humbling realization is how these jets shape the universe around them. By dumping energy into the space between galaxies, they can heat entire galaxy clusters, preventing gas from cooling and forming new stars. In a way, quasar jets are the universe's ultimate regulators, capable of turning entire regions into stellar nurseries or cosmic dead zones. And somewhere out there, right now, a jet from a supermassive black hole is carving its path through the cosmos, etching its story across the fabric of spacetime itself. There's a special kind of cosmic violence that unfolds when a star wanders too close to a black hole, a fate so brutal it stretches the very meaning of destruction. Picture this: a sun-like star minding its own business gets lured in by a black hole's gravitational pull. As it crosses the point of no return, the tidal forces, the difference in gravity between the star's near and far sides becomes so extreme that the star isn't just torn apart. It's spaghettified, stretched into a thin, glowing strand of plasma before being devoured. This isn't science fiction. It's a tidal disruption event, one of the universe's most spectacular and terrifying light shows. Take Assassin 15 LH, a flare spotted in 2015 that briefly outshone every star in its host galaxy combined. At first, astronomers thought they were looking at the brightest supernova ever recorded, a staggering explosion 100 times more luminous than a typical stellar death. But as the data rolled in, something didn't add up. Supernova fade predictably while this flare flickered erratically, its light curve dancing to a rhythm no dying star could produce. The culprit, a supermassive black hole hidden in the galaxy's core, shredding a passing star like cosmic confetti. The glow wasn't from a collapsing star. It was the last, desperate scream of stellar matter being ripped apart at the atomic level, heated to millions of degrees as it spiraled into oblivion. What makes these events so mesmerizing isn't just the violence, it's the aftermath. As the black hole feasts, it doesn't swallow everything at once. Some of the star's debris gets flung outward in colossal jets, while the rest forms a temporary accretion disk glowing white-hot from friction. This disk acts like a cosmic bonfire, radiating energy across the electromagnetic spectrum. In a Saturn 15LH's case, the flare was so bright it temporarily blinded telescopes, peaking at over 570 trillion times the luminosity of our Sun. To put that in perspective, if this event had happened in our Milky Way, it would have outshone the full moon, casting shadows on Earth at night. Yet tidal disruptions aren't just about destruction, they're also cosmic recycling plants. The shredded star's material doesn't vanish. Instead, it enriches the black hole's surroundings, seeding future generations of stars and planets with heavy elements. Some theories even suggest these events could trigger star formation in otherwise dormant galaxies, like a shockwave jump-starting a stellar nursery. But perhaps the most haunting detail is how common these events might be. Astronomers estimate that a star gets spaghettified by a supermassive black hole once every 10,000 to 100,000 years in a typical galaxy. Given the billions of galaxies out there, that means somewhere, right now, a star is meeting its end in the most extreme way possible, stretched, shredded, and set ablaze by forces beyond comprehension. And with every new detection, we're peeling back the curtain on these hidden monsters, revealing how black holes don't just lurk in the dark. They actively shape the cosmos, one stellar meal at a time. In the grand cosmic fireworks display, some stars don't just explode, they vanish without a trace. Enter pair instability supernovas, the universe's ultimate disappearing act. These rare cataclysms occur when stars between 130 and 250 times the mass of our Sun reach the end of their lives, detonating with such ferocity that they obliterate themselves completely. No black hole, no neutron star, just an empty void where a stellar giant once burned. The physics behind this annihilation is as elegant as it is catastrophic. At the core of these supermassive stars, temperatures soar so high that gamma-ray photons, normally harmless carriers of light, transform into something far more destructive. When these photons collide, they spontaneously spawn pairs of electrons and their antimatter counterparts, positrons. This conversion robs the star's core of the radiation pressure needed to resist gravity's relentless pull. Suddenly unsupported, the core collapses inward, heating up even further until it triggers runaway nuclear fusion. The result, a thermonuclear detonation so powerful it doesn't just blow off the star's outer layers, it vaporizes the entire structure, scattering its guts across light years of space in an explosion bright enough to outshine entire galaxies for months. What makes these events so puzzling is their scarcity in the modern universe. Pair instability supernovas are thought to be relics of the cosmos's wild youth, when the first generations of stars, made from pure hydrogen and helium, grew to monstrous sizes. Today, heavier elements in stars help regulate their internal temperatures, making it nearly impossible for them to reach the critical mass needed for this self-destruct sequence. But in the early universe, lacking these heavier elements, stars could balloon to sizes that made them walking time bombs. When they finally detonated, they didn't just vanish. They seeded the cosmos with the first heavy elements, forging the raw materials for future stars, planets, and even life itself. One of the most tantalizing clues to their existence lies in distant clouds of iron drifting between galaxies. Astronomers have found vast reservoirs of this metal in regions where no known supernova type could have produced it unless pair instability explosions were at work. These cosmic iron deposits, some containing enough material to build millions of Earths, might be the long-cooled remnants of primordial stars that erased themselves from existence. Yet for all their destructive power, pair instability supernovas may have played a constructive role in shaping the universe we know. By spewing heavy elements into the void, they provided the building blocks for everything that followed: second-generation stars, rocky planets, and eventually the chemistry of life. Some theories even suggest these explosions helped reionize the early universe, clearing the cosmic fog that once shrouded all of space. While no one has definitively observed a pair instability supernova in action, astronomers are hunting for their fingerprints in the farthest reaches of space, where the light of ancient explosions still lingers after billions of years. Each potential candidate offers a glimpse into a time when the universe was younger, hotter, and far more volatile, a time when stars didn't just die, but erased themselves from the cosmic ledger in blazes of unimaginable glory. Deep in the heart of our galaxy, something mysterious is glowing. An unexplained fountain of gamma rays at precisely 511 kilo-electron volts, pouring out from the Milky Way's core like a cosmic beacon. This isn't just random noise, it's a signal so consistent that astronomers have been puzzling over it for decades. What could possibly produce such a specific, energetic signature? One tantalizing possibility takes us into the shadowy realm of dark matter, the invisible glue holding galaxies together. If certain theories are correct, this gamma-ray excess could be the first indirect evidence of dark matter particles annihilating each other in the depths of space. The idea hinges on a type of dark matter candidate called weakly interacting massive particles, or WIMP. According to some models, when these hypothetical particles collide, they could annihilate on contact, converting their mass into energy and producing a burst of gamma rays, including photons at that exact 511 kilo-electron volt mark. It's like cosmic detective work. If dark matter is made of WIMP, and if those WIMP are concentrated near the galaxy's center, as simulations suggest they should be, then their mutual destruction could theoretically explain the eerie glow we're observing. But the plot thickens. Not everyone's convinced. Alternative explanations range from more mundane astrophysical sources, like a swarm of microquasars or pulsars, to even stranger possibilities involving primordial black holes. What makes the dark matter hypothesis so compelling, though, is its elegance. The Milky Way's core is thought to be dense with dark matter, creating the perfect environment for frequent particle collisions. If even a tiny fraction of those collisions resulted in annihilation, the energy released could match the observed signal. It's like standing outside a darkened room, hearing the faint sound of breaking glass, and theorizing that someone inside might be smashing wine bottles, except in this case, the bottles are particles we've never directly seen. The implications are staggering. If confirmed, this could crack open one of astronomy's greatest mysteries, revealing not just the nature of dark matter, but also how it shapes the universe around us. Picture a hidden particle, invisible to all our telescopes, finally betraying its presence through the faintest flash of light. And while the jury's still out, science demands more evidence. The hunt for answers continues, with newer telescopes and detectors scouring the galaxy for clues. Until then, that unexplained glow remains a siren call, drawing us deeper into the cosmos's darkest secrets. Our sun may seem like a calm, steady presence until it isn't. Every so often, it unleashes solar flares, violent bursts of radiation that can disrupt satellites, knock out power grids, and paint the skies with dazzling auroras. But as disruptive as these eruptions can be, they're nothing compared to the cosmic monsters known as superflare stellar tantrums, so powerful they could cook a planet's atmosphere to a crisp. Imagine a flare not just strong enough to interfere with radio signals, but one capable of ionizing an entire world's upper atmosphere, stripping away its protective layers over centuries and turning a habitable paradise into a barren wasteland. Shockingly, these aren't just theoretical nightmares. Telescopes like Kepler have caught distant stars unleashing flares 10,000 times more energetic than anything our sun has ever produced. The difference between a typical solar flare and a superflare boils down to raw energy. A standard solar flare might release the equivalent of 1 billion megaton bombs in mere minutes, enough to trigger geomagnetic storms on Earth. But superflares, they're in another league entirely. Kepler's observations revealed stars blasting out flares with energy surpassing 10 to the 34 joules, enough power to boil Earth's oceans in hours if we were orbiting one of those stars. What's truly unsettling is that many of these superflare stars aren't exotic oddballs. They're often similar to our Sun in size and age, suggesting our own star might not be as benign as we'd like to think. So why doesn't our Sun behave this way? The answer lies in its magnetic personality. Solar flares happen when twisted magnetic field lines near sunspots snap like overstretched rubber bands, releasing pent-up energy. Superflares, on the other hand, seem to require far more intense magnetic activity. Think starspots larger than entire suns, or magnetic fields tangled into knots of unimaginable complexity. Young, rapidly spinning stars are especially prone to these outbursts, their dynamos churning out chaos as they whirl like cosmic tops. But even middle-aged stars like ours might not be immune. Geological records hint at a potential superflare event around 7,000 years ago, detected in radioactive isotopes buried in ice cores, a ghostly whisper of a time when our Sun might have briefly gone rogue. The real question isn't just could it happen again, it's what would happen if it did. A modern superflare aimed at Earth wouldn't just fry electronics, it could trigger a cascade of atmospheric chemistry, breaking down ozone and exposing life to deadly ultraviolet radiation. Over centuries, the steady erosion could mimic the fate of Mars, which lost its protective magnetic field and much of its atmosphere to the solar wind. Yet there's a silver lining. Superflares might also be cosmic matchmakers, their radiation potentially kickstarting chemistry in the atmospheres of distant exoplanets, creating the building blocks for life even as they threaten to destroy it. As telescopes grow more advanced, we're catching these stellar outbursts in unprecedented detail, watching as stars across the galaxy remind us of their raw, untamed power. And while our Sun remains relatively well-behaved for now, its quieter nature might be the exception rather than the rule, a humbling reminder that in the grand tapestry of the universe, even the most familiar stars can harbor surprises. Picture a galaxy where every star, every planet, every fleck of cosmic dust is rendered invisible, not by darkness, but by a single point of light so brilliant it drowns out everything else. This is the reality of an active galactic nucleus, or AN, a phenomenon where a supermassive black hole transforms its entire host galaxy into the universe's most dazzling spotlight. At the heart of these cosmic powerhouses, black holes weighing billions of suns don't just lurk, they feast, pulling in torrents of gas and dust so violently that the friction heats the infalling material to millions of degrees. The result, a glow so intense it can outshine the combined light of every star in the galaxy for millions of years. These aren't just black holes, they're cosmic engines. As matter spirals toward the event horizon, some of it gets funneled into jets that blast outward at nearly the speed of light, piercing through intergalactic space like twin lasers. But it's the energy radiating from the accretion disk, the swirling maelstrom of doomed material, that truly defies belief. A single AGN can emit more energy in 1 second than our Sun will produce in its entire lifetime. Some of these objects, called quasars, are so luminous they're visible from the edge of the observable universe, their light traveling for billions of years before reaching our telescopes. What's even more fascinating is how these titanic outbursts shape their surroundings. The radiation pouring from an AGN is so intense it can sterilize entire swaths of its host galaxy, stripping atmospheres from planets and preventing new stars from forming. Yet paradoxically, these same forces might also trigger star birth in distant regions, as shockwaves compress gas clouds into stellar nurseries. It's a cosmic push and pull, destruction and creation orchestrated by a single, insatiable gravitational monster. The most extreme examples, known as blazars, take this violence to another level. When one of those relativistic jets happens to point directly at Earth, the effect is like staring down the barrel of a particle accelerator. The jet's light gets amplified by its own motion, blue-shifted into a lethal barrage of gamma rays and X-rays. If a nearby galaxy hosted a blazar aimed our way, its radiation could strip Earth's ozone layer in days. Thankfully, the closest known blazar lies hundreds of millions of light-years away, a reminder that the universe's most dazzling light shows are best admired from a distance. Yet for all their destructive potential, AGNs serve a crucial role in the cosmic ecosystem. By redistributing energy and heavy elements across vast distances, they help regulate the growth of galaxies and clusters. Some theories even suggest that without these outbursts, galaxies like our Milky Way might never have formed, their black holes acting as both destroyers and architects of the large-scale universe. And as astronomers peer deeper into space, they're finding that AGNs were far more common in the early universe, a time when black holes and galaxies grew up together in a fiery dance of mutual annihilation and rebirth. So the next time you look up at the night sky, remember, somewhere out there, a galaxy is burning brighter than 1 trillion suns, its heart a supermassive black hole turning matter into light on a scale that defies imagination. And in that brilliance, we're glimpsing the universe's most extreme balancing act, the delicate equilibrium between gravity's appetite and the light that escapes it. Most supernovae are spectacular enough, but some take violence to another level by hurling debris at nearly the speed of light. Meet the relativistic supernova, a rare breed of stellar explosion where the dying star doesn't just burst apart. It launches jets of material so fast they could lap Earth 7 times in a single second. Take SN 2009 one of the first confirmed examples of this extreme phenomenon. Unlike a typical core collapse supernova, where the star's outer layers rebound off an imploding core, this explosion showed clear signatures of a central engine, likely a newly formed neutron star or black hole actively funneling energy into narrow, ultra-fast jets. What makes these events so extraordinary is their power source. In a normal supernova, the energy comes almost entirely from the initial shockwave of the collapsing core. But in engine-driven explosions like SN 2009 the newborn compact object at the heart of the blast keeps pumping energy into the system like a cosmic afterburner. Magnetic fields and rapid rotation combine to accelerate particles to relativistic speeds, creating jets that punch through the stars remains with enough force to shape the entire explosion. These aren't just expanding balls of debris, they're focused, high-energy beams carving their way through space. The evidence for this came from radio observations. As the jets plowed into surrounding gas, they generated shock waves that produced intense synchrotron radiation, a telltale glow caused by electrons spiraling at near-light speed around magnetic field lines. This emission was far brighter and more long-lived than anything a typical supernova could produce, pointing to a persistent energy source at work. Even more telling was the polarization of the light, which revealed the presence of highly ordered magnetic fields, exactly what you'd expect from a collimated jet rather than a chaotic spherical explosion. But here's where these events get even stranger. While most relativistic supernovae are linked to long gamma-ray bursts, those spectacular cosmic fireworks we discussed earlier SN 2009 defied expectations by producing no detectable gamma radiation. This suggested its jets might have been weaker, narrower, or perhaps buried too deep in the star to break free cleanly. It's like comparing a blowtorch to a laser. Both are focused streams of energy, but one penetrates further while the other dumps its energy closer to home. The implications stretch far beyond just cataloging exotic stellar deaths. These engine-driven explosions are cosmic foundries, forging heavy elements in their jets and scattering them across galaxies. Some theories suggest they might even be responsible for certain types of mysterious fast radio bursts, those fleeting intergalactic signals that have puzzled astronomers for years. And because their jets carry clues about the physics of newborn neutron stars and black holes, each new discovery helps unravel how matter behaves under conditions impossible to replicate on Earth. So the next time you hear about a supernova, remember, some aren't just stars dying, but stellar engines roaring to life, proving that even in destruction, the universe finds ways to push the limits of what's possible. And with every new observation, we're decoding how these extreme events shape the cosmos, one relativistic blast at a time. Rising from the heart of the Milky Way like ghostly titans, two colossal bubbles of gamma rays stretch halfway across our galaxy, each one towering 25,000 light-years above and below the galactic plane. Discovered by NASA's Fermi Gamma Ray Space Telescope in 2010, these enigmatic structures, now known as the Fermi Bubbles, defy easy explanation, their crisp edges and sheer scale pointing to a cataclysmic event in our galaxy's past. Picture two colossal orbs, each large enough to swallow 1,000 solar systems side by side, glowing with high-energy radiation that betrays a violent origin. The leading theory suggests these bubbles are scars from an ancient feeding frenzy by Sagittarius, a star, the supermassive black hole anchoring our galaxy. Around 4 million years ago, around the time early hominids walked the Earth, this dormant beast may have briefly awakened, consuming a massive clump of gas or even a star. The resulting energy release could have blasted twin jets of charged particles straight up and down through the galaxy's poles, leaving behind these lingering gamma-ray monuments. It's the cosmic equivalent of a volcanic eruption's ash cloud, only instead of dust, these bubbles are filled with ultra-relativistic particles still zipping around at near light speed millions of years later. But there's a twist. Some astrophysicists argue the Fermi bubbles might instead be remnants of multiple supernova explosions from a burst of star formation in the galactic center. When massive stars die in quick succession, their combined shockwaves can carve out vast structures in the surrounding gas. Yet the Fermi bubbles' symmetry and pristine edges tilt the scales toward a single, colossal event, something with the focused power of a black hole eruption rather than scattered stellar deaths. What makes these structures so fascinating isn't just their size, it's what they reveal about our galaxy's hidden volatility. The Milky Way seems calm today, but the Fermi bubbles prove it was once a far more tempestuous place, capable of unleashing energies that would make modern supernova look like firecrackers. And they're not entirely dormant even now. Observations show the bubbles' edges emit faint X-rays, suggesting ongoing interactions with the galaxy's halo gas, like smoke rings slowly dissipating in a cosmic breeze. Perhaps most intriguing is what this means for life in the galaxy. If such an eruption occurred relatively recently by cosmic standards, could it happen again? A similar outburst today, with its intense radiation directed along the galactic plane, might sterilize vast swaths of the Milky Way. It's a humbling reminder that even our seemingly peaceful galactic neighborhood has a violent streak, one whose echoes we're only beginning to decode, written in gamma rays across the sky. Among the universe's most mysterious signals, few are as baffling or as powerful as fast radio bursts. These fleeting blips of cosmic radio noise last just milliseconds, yet in that blink of an eye, they discharge as much energy as our sun pumps out over an entire month. Imagine compressing all the sunlight that falls on Earth over 30 days into a burst shorter than a camera flash. That's the staggering efficiency of an FRB. For years, these signals came exclusively from distant galaxies, their origins buried in layers of speculation. Were they colliding neutron stars, alien transmissions, the dying screams of evaporating black holes? Then in 2020, everything changed when astronomers caught one erupting inside our own Milky Way, tracing it back to a known magnetar called SGR 1935 plus 2154. The detection was a watershed moment. For the first time, scientists could study an FRB's birthplace up close, linking it definitively to one of the most extreme objects in existence. When this particular magnetar, already infamous for its violent outbursts, unleashed a milliseconds-long radio burst, telescopes worldwide swung into action. What they found confirmed suspicions while raising new questions. The signal's polarization revealed twisted magnetic fields trillions of times stronger than Earth's, suggesting the burst was generated by a starquake so powerful it momentarily cracked the magnetar's crust. Think of it like snapping a colossal rubber band. The snap releases pent-up energy in a sharp, focused pulse. Yet perplexingly, not all of this magnetar's eruptions produced FRBs, hinting that some critical threshold of magnetic instability must be crossed to trigger these cosmic radio fireworks. What makes FRBs particularly fascinating is how they illuminate the invisible. As these bursts race across intergalactic space, they interact with electrons in their path, subtly slowing different radio frequencies at varying rates. By measuring this dispersion, astronomers can map the universe's hidden matter, the diffuse gas between galaxies that's nearly impossible to detect otherwise. It's like using a flashlight beam to reveal dust in a dark room. Each FRB's journey encodes a snapshot of the cosmic web it traversed, but the 2020 event added another layer. Unlike distant FRBs that often repeat unpredictably, our homegrown burst was a one-off, suggesting magnetars might produce both repeating and non-repeating varieties through different mechanisms. Some theorists now propose that younger, more active magnetars generate singular, cataclysmic FRBs during rare crust-shattering quakes, while older, calmer ones emit weaker, repeating bursts as their magnetic fields slowly unwind. This could explain why most extragalactic FRBs remain silent after their initial blast. Their engines might be spent after one titanic convulsion. The implications stretch far beyond just solving an astronomical puzzle. If magnetars are indeed the primary source of FRBs, their bursts could serve as cosmic lighthouses, helping measure the expansion rate of the universe with unprecedented precision. They might even reveal the nature of dark matter, should their signals interact with invisible particles on their journey through space. And with every new detection, whether from our galactic backyard or the edge of the observable universe, we're piecing together how these ephemeral sparks illuminate the most violent magnetic extremes of existence. In 1991, a cosmic ray detector in Utah recorded something that sent shockwaves through the world of physics. A single subatomic particle screaming through Earth's atmosphere with so much energy, scientists initially thought the readings must be wrong. Nicknamed the "Oh my God" particle, this ultra-high-energy cosmic ray packed an unprecedented 320 exa-electronvolts of energy, equivalent to a baseball traveling at 60 miles per hour, condensed into a speck smaller than an atom. To grasp how absurd that is, consider this: the Large Hadron Collider, humanity's most powerful particle accelerator, can only propel particles to a fraction of that energy, about 7,000 times less. So where could such a particle possibly come from? That's the million-dollar question. The sheer energy of the "Oh my God" particle defies known astrophysical processes. Even supermassive black holes and gamma-ray bursts struggle to explain it. Based on our current understanding, cosmic rays this energetic should have lost momentum long before reaching Earth, scattered by interactions with the cosmic microwave background, the faint afterglow of the Big Bang. It's like throwing a paper airplane into a hurricane and expecting it to land perfectly intact on the other side of the planet. Yet here it was, slamming into our atmosphere with the force of a knuckleball thrown by a cosmic pitcher we can't even locate. The mystery deepens when you realize we still don't know its origin. Unlike light, cosmic rays don't travel in straight lines. Their paths get bent by magnetic fields as they zip through space, making it nearly impossible to trace them back to their source. The "Oh my God" particle could have been flung our way by a hyperactive galactic nucleus, a colliding galaxy cluster, or something even more exotic, like a crack in spacetime itself. Some theories even suggest these ultra-high-energy particles might be the fingerprints of dark matter annihilations or defects in the fabric of the universe left over from its earliest moments. What's truly humbling is how rare these events are. In the 3 decades since that first detection, only a handful of similar particles have been recorded, each one arriving with no warning and vanishing just as quickly. They're like cosmic lightning strikes, impossible to predict, fleeting, and utterly devastating to our current models of physics. Yet with every new detection, we edge closer to understanding what kind of cosmic powerhouse could accelerate matter to such mind-bending speeds. For now, the oh my god particle remains one of astronomy's great unsolved riddles, a tiny messenger from the far reaches of the universe carrying secrets we're still struggling to decode. And somewhere out there, another one might be racing toward Earth right now, ready to shatter our assumptions all over again. Picture the entire universe as we know it, every galaxy, every star, every atom, instantaneously rewritten by a single, unstoppable wave of annihilation. This isn't the plot of a sci-fi horror story. It's the spine-chilling hypothesis known as vacuum decay, a quantum doomsday scenario where the very fabric of reality could unravel in a flash. At its core, this idea hinges on an unsettling possibility. What if the universe isn't in its most stable state? What if our cosmos is perched precariously on a quantum ledge, like a marble balanced at the top of a hill, waiting for the slightest nudge to come crashing down into a lower, more stable energy state? The physics behind this hinges on something called the Higgs field, an invisible energy field that permeates all of space, giving particles their mass. Right now, this field exists in what scientists call a false vacuum, a state that appears stable but might not be the lowest possible energy configuration. If somewhere in the universe this field were to suddenly tunnel into a true vacuum state, it could trigger a cascading transformation. A bubble of this new, more stable reality would expand outward at the speed of light, rewriting the fundamental laws of physics as it goes. Inside this bubble, atoms might cease to hold together, forces like gravity and electromagnetism could vanish or distort, and the universe as we know it would effectively end, not with a bang, but with a silent, inescapable rewrite of existence itself. Here's where it gets even more unnerving. Because this wave would move at light speed, there'd be no warning. One moment, everything would be normal. The next, an invisible wall of annihilation would erase physics as we understand it. Even if this bubble began on the far side of the observable universe, we'd never see it coming. No light, no signal, no distress call could outrun it. By the time the edge reached us, it would already be too late. The only silver lining, if it happened, it would be instantaneous, no pain, no fear, just an abrupt end to reality itself. But before you panic, consider this. Scientists widely debate whether such an event is even possible. Some argue the universe's current vacuum state is likely stable, having lasted billions of years without decay. Others point out that high-energy experiments like the Large Hadron Collider briefly create conditions trillions of times more extreme than anything in nature, and so far no vacuum bubbles have emerged. Still, the mere possibility serves as a humbling reminder of how little we truly understand about the universe's deepest rules, and how much power might still lie hidden in the quantum shadows. This idea isn't just theoretical nightmare fuel, it's a frontier of modern physics. Researchers actively study high-energy particle collisions and cosmic observations for any hint of vacuum instability. Some even speculate that if we could detect the faintest ripples in the Higgs field, we might one day predict or even prevent such an event. Until then, vacuum decay remains one of the most awe-inspiring and terrifying what-ifs in science, a testament to the universe's capacity for both wonder and absolute unfathomable change. Some black holes don't fade quietly into the cosmic background. They go out with a bang that could briefly outshine entire galaxies. According to Stephen Hawking's groundbreaking theory, black holes aren't completely black after all. Through quantum effects at their event horizons, they slowly leak radiation and lose mass over time. For most black holes we know about, those with masses several times that of our Sun, this evaporation process takes longer than the current age of the universe. But there's a fascinating exception: hypothetical primordial black holes, tiny relics that might have formed in the seething chaos of the Big Bang itself. These ancient cosmic cinders could be as small as a mountain yet pack the mass of an asteroid. Due to their diminutive size, their evaporation would accelerate exponentially as they shrank. In their final seconds, a black hole weighing 1 billion tons would release as much energy as 1,000,001 megaton nuclear bombs detonating simultaneously, all focused into a brilliant burst of gamma rays. Picture the most powerful cosmic explosion imaginable, squeezed into a volume smaller than an atom before vanishing completely. This is Hawking radiation's ultimate prediction. Not just a quiet whisper of particles, but a screaming finale of light so intense it could be detected across the observable universe. Astronomers have been hunting these telltale flashes for decades, scanning gamma-ray data for the unique fingerprint of a dying primordial black hole. The signature would be unmistakable, an impossibly brief spike of high-energy photons coming from nowhere in particular, lasting just milliseconds before disappearing forever. Unlike gamma-ray bursts from colliding stars or supernova, these events wouldn't have any afterglow or host galaxy. They'd simply be solitary death cries echoing from the dawn of time itself. What makes this search so compelling is what it could reveal about the early universe. If we ever detected such an explosion, it would confirm the existence of primordial black holes and possibly solve multiple cosmic mysteries at once. Some theories suggest these tiny black holes could account for part of the elusive dark matter that shapes our universe's structure. Others propose they might be the seeds of supermassive black holes that now anchor galaxies, having grown over billions of years. But the hunt isn't easy. Current telescopes might only spot these explosions if they occur relatively nearby in cosmic terms, within a few 100 million light-years. More sensitive detectors could change that, listening for the last cries of black holes evaporating in the farthest reaches of space. Every unexplained gamma-ray flash brings us closer to answering one of cosmology's most intriguing questions. Did the Big Bang leave behind a hidden population of tiny black holes, and are they blinking out of existence all around us in bursts of light we've yet to notice? For now, the search continues, with scientists sifting through data from gamma-ray observatories like Fermi and Swift, waiting for that telltale flash that could rewrite our understanding of both black holes and the universe's birth. Each time a satellite detects an unaccounted burst of gamma rays, there's a brief moment of excitement. Could this be it? The final, defiant explosion of a black hole that's been silently evaporating since the first moments of time. Until that day comes, these hypothetical detonations remain one of theoretical physics' most spectacular unconfirmed predictions, a reminder that even in death, the universe's most mysterious objects refuse to go quietly. When black holes collide, they don't just send ripples through space, they shake the very fabric of the universe. Gravitational wave detectors like LIGO have captured the mergers of stellar mass black holes, events so violent they briefly outshine all the stars in the observable universe combined. But scale that up to supermassive black holes, the billion solar mass giants lurking at the hearts of galaxies, and the numbers become almost incomprehensible. A single collision between two of these cosmic titans would unleash more energy than 100 billion supernova, radiating gravitational waves so powerful they could warp spacetime across billions of light-years. The physics behind these mergers is mind-bending. As two supermassive black holes spiral toward each other, their immense gravity distorts the surrounding space, creating a whirlpool of twisted spacetime. Gas and stars caught in this maelstrom heat up to trillions of degrees, lighting up the galactic center like a beacon. but the real spectacle begins when the black holes finally merge. In the last seconds before collision, they orbit each other hundreds of times per second, churning out gravitational waves with frequencies so low they could make entire solar systems vibrate like tuning forks. The final merger itself lasts mere milliseconds, yet in that instant it converts a significant fraction of the black hole's combined mass into pure gravitational energy equivalent to several suns vaporized into ripples in spacetime. What's truly staggering is how these waves propagate. Unlike light, which can be absorbed or scattered, gravitational waves travel almost unimpeded across cosmic distances. A supermassive black hole merger in a distant galaxy would flood the universe with waves stretching light years in wavelength, subtly squeezing and stretching everything in their path, including Earth. Future observatories like pulsar timing arrays are poised to detect these cosmic tremors by monitoring the precise flashes of millisecond pulsars, the universe's most accurate clocks. If the rhythm of these pulsars falters by even a few nanoseconds, it could signal the passage of a gravitational wave from a collision that happened when the universe was half its current age. The implications go beyond just detecting distant cataclysms. These mergers could explain how supermassive black holes grow to such enormous sizes and why nearly every large galaxy seems to host one. Some theories suggest these collisions might also eject merged black holes from their host galaxies at speeds reaching thousands of kilometers per second, leaving behind a trail of disrupted stars and gas. Others speculate that the gravitational waves from these events could carry echoes of extra dimensions or even clues about dark matter. While we haven't yet detected a supermassive black hole merger directly, the first hints might already be hiding in pulsar data. When that discovery comes, it won't just be a footnote in astrophysics. It'll rewrite our understanding of how the universe's most massive objects shape the cosmos around them. And as our detectors grow more sensitive, we might soon find ourselves listening to the echoes of collisions so vast, they make the Big Bang itself seem small. On December 25, 2010, astronomers received an unexpected cosmic gift, a gamma-ray burst so unusual it earned the nickname the Christmas burst. Unlike typical GRBs that last mere seconds or minutes, this event, catalogued as GRB 101225A, blazed across the sky for a puzzling 28 minutes, defying every classification scientists threw at it. At first glance, it resembled a long gamma-ray burst from a collapsing star, but the energy signature didn't match. Then came the real twist. The afterglow flickered like a dying ember, fading and brightening in a way no supernova or kilonova could explain. One leading theory suggests this burst might have been caused by something far more exotic, an asteroid-sized chunk of dense metallic material slamming into a neutron star at a fraction of light speed. Picture a cosmic wrecking ball, perhaps the shattered remnant of a white dwarf or the iron core of a dead star, plowing into a city-sized stellar corpse with the mass of a sun. The impact would release an explosion of energy as the neutron star's immense gravity violently shredded the incoming object, creating a fireball of superheated debris. Unlike the clean, symmetrical jets of a typical GRB, this chaotic collision could explain the burst's erratic behavior, like tossing a log onto a bonfire and watching it sputter unpredictably as it burns. What makes the Christmas burst even more intriguing is the redshift riddle. Initial measurements placed it impossibly close, just a few thousand light-years away in our own galaxy, which would have made it bright enough to outshine the full moon. Later analysis pushed its origin much farther out, somewhere beyond 1 billion light-years, but even that raised questions. If it was truly that distant, how did it sustain such a long, luminous afterglow? Some astronomers speculate the neutron star might have been wrapped in a cocoon of dense debris, prolonging the light show as the shockwaves bounced around inside before finally escaping. The event's legacy lives on as a reminder of how much we still don't understand about the universe's most violent phenomena. Most GRBs fit into neat categories, but outliers like the Christmas burst force scientists to rethink their models. Could there be an entire zoo of exotic, ultra-rare collisions we've yet to discover? Neutron stars tearing apart comets, black holes shredding rogue planets, or other scenarios we haven't even imagined. Every unexplained flash in the data is a clue, a whisper from the cosmos that the rulebook isn't complete yet. For now, GRB 101225 remains one of astronomy's most delightful puzzles, a gift that keeps on giving long after the holiday decorations are packed away. And as telescopes grow more sensitive, who knows what other cosmic surprises might be waiting, wrapped in the darkness of space, ready to rewrite the story of how the universe's most energetic explosions work. Wolf-rayet stars are the universe's ticking time bombs, massive, unstable giants that tear themselves apart long before their final demise. These rare celestial beasts, named after the astronomers who first identified their strange spectra, represent the final, tumultuous stage in the lives of stars at least 20 times heavier than our Sun. What makes them unique isn't just their size, but their death throes. They essentially commit stellar suicide by stages, violently ejecting their own outer layers through hurricane-force stellar winds. Picture a cosmic onion unraveling at 1,000,000 miles per hour, shedding its hydrogen skin until only a searing core of helium, carbon, and heavier elements remains. This self-destructive process leaves behind some of the hottest known star surfaces in the universe, blazing at over 200,000 degrees Fahrenheit, so intense they glow blue-white like a welder's torch against the blackness of space. The real fireworks begin when these exposed cores finally collapse. Unlike typical supernova, where massive stars explode with their hydrogen envelopes intact, wolf-rayet stars detonate as bare, ultra-dense nuclei. This stripped-down state allows their deaths to unfold with terrifying efficiency when their cores implode. The resulting explosions can channel energy into narrow, ultra-relativistic jets rather than dissipating it in all directions. Under the right conditions, this focused fury could produce a gamma-ray burst aimed like a celestial sniper rifle across interstellar space. That's where WR104 enters the story. Located about 8,000 light-years away in the constellation Sagittarius, this binary wolf-rayet system has astronomers watching with bated breath. Its pinwheel-like dust plumes, visible in infrared images, betray the presence of not one but two massive stars locked in a gravitational dance, and one partner is a wolf-rayet teetering on the edge of collapse. What makes WR104 particularly noteworthy is its orientation. Current observations suggest one of its poles may be pointed roughly toward Earth. If, and it's still a big if, this star collapses into a gamma-ray burst along its rotational axis when its time comes, the resulting beam of radiation could deliver a devastating payload to our solar system. Calculations suggest such an event, even from 8,000 light-years away, might strip Earth's ozone layer for years, exposing life to deadly ultraviolet radiation. The good news, most estimates give WR104 at least another 100,000 years before reaching critical instability. The better news, gamma-ray bursts are exceptionally rare in our galactic neighborhood, with odds favoring that any future burst's deadly beam would miss us entirely. Still, WR104 serves as a sobering reminder that we live in a cosmic shooting gallery, where distant stellar catastrophes could one day reach across the void with consequences no civilization could ignore. Beyond their destructive potential, wolf-rayet stars play a crucial role in galactic chemistry. Their furious winds blast heavy elements like carbon and oxygen into interstellar space at phenomenal rates. A single wolf-rayet can eject an entire sun's worth of processed material in just 100,000 years. This enriched debris becomes the raw material for future stars, planets, and even life. Some studies suggest our own solar system might owe its existence to the heavy element legacy of long-dead wolf-rayet ancestors. These stars don't just destroy, they create, scattering the atomic ingredients for new worlds across the cosmos in their final, fiery breaths. For astronomers, wolf-rayet systems offer a front-row seat to stellar evolution's most extreme chapters. Their short lifespans, just a few million years compared to our Sun's 10-billion-year existence, make them cosmic mayflies, here today and gone tomorrow by galactic standards. Yet in that brief time, they shine with the brilliance of millions of suns, sculpting their surroundings with shockwaves and radiation before ending their lives in explosions that echo across the universe. Whether as potential gamma-ray burst progenitors or galactic alchemists, wolf-rayet stars remind us that in the cosmos, even destruction serves a purpose, scattering the seeds of new beginnings amid the ashes of stellar giants. The fabric of spacetime might seem smooth and unbroken, but hidden within it could be cosmic scars left over from the universe's birth, defects known as cosmic strings. These hypothetical remnants from the Big Bang are thought to be unimaginably thin, yet denser than neutron stars, stretching across the cosmos like invisible threads. If they exist, they'd be under such immense tension that even a single inch of cosmic string could weigh as much as Mount Everest. Now picture one of these ultra-dense filaments suddenly snapping. The energy released in that instant would dwarf entire supernova, creating shockwaves capable of warping spacetime itself. What makes cosmic strings so bizarre is how they distort reality around them. The extreme mass density concentrated in these thread-like defects would bend light like a funhouse mirror, creating double images of distant galaxies or strange, elongated shapes in the cosmic background. Unlike black holes, which warp spacetime into a bottomless pit, cosmic strings would slice through it like a razor, leaving behind a unique signature, a sudden jump in the apparent position of stars or galaxies as their light passes on either side of the string. It's as if the universe itself developed a crack, and everything we see near it gets subtly fractured. Theoretical models suggest that if two cosmic strings crossed or a closed loop of string collapsed, the resulting energy release could briefly outshine all the stars in the observable universe combined. The mathematics behind these events reads like something from science fiction. Spacetime itself would recoil from the rupture, emitting gravitational waves so powerful they could momentarily shake the entire cosmos. Some calculations even suggest these snaps could create high-energy particle jets similar to those from black holes, pouring radiation into intergalactic space. Yet for all their destructive potential, cosmic strings might also serve as cosmic signposts. If detected, their distinctive light-bending effects could help map the universe's large-scale structure. Some theories even propose that these relics from the universe's infancy might have seeded the formation of galaxies, their gravitational influence acting as scaffolding around which matter first clustered. The hunt for cosmic strings continues, with astronomers scanning detailed maps of the cosmic microwave background for telltale distortions. While none have been found yet, their possible existence reminds us that the early universe was a far stranger place than we can imagine, a place where defects in spacetime itself might still linger, silent and invisible, until the moment one finally snaps and sends shockwaves through the cosmos. In June 2018, astronomers spotted something bizarre, a cosmic flare so unusual it earned the nickname the Cow. Officially designated at 2018 Cow, this event didn't behave like anything scientists had seen before. Most supernovae take weeks to reach peak brightness, but the Cow erupted in just days, shining 100 times brighter than a typical stellar explosion. Then, instead of fading gradually, it lingered for months, pumping out bizarre pulses of X-rays and radio waves, as if something inside was refusing to die quietly. What made this explosion so baffling? For starters, its light curve defied all expectations. Normal supernovae get their energy from radioactive decay, producing a predictable pattern of brightening and dimming. The cow's light didn't follow that script. It was too blue, too fast, and packed with high-energy radiation that suggested something far more exotic was at play. One leading theory points to a black hole or neutron star being born in real time. Imagine a massive star collapsing, not into a clean supernova, but into a black hole that immediately starts devouring the surrounding stellar debris. The infalling material would form a swirling accretion disk, glowing white-hot as it's torn apart by gravity, while twin jets of particles scream outward at nearly light speed. This engine-powered explosion could explain the cow's persistent energy output, like a cosmic afterburner refusing to shut off. But there's a wilder possibility. The cow might have been a white dwarf torn apart by an intermediate mass black hole. Picture a dead star, a dense Earth-sized ember, wandering too close to a black hole weighing thousands of solar masses. The tidal forces would shred the white dwarf like tissue paper, igniting a thermonuclear fireball as its material crashes together in the black hole's grip. This scenario could account for the event's unusual chemical fingerprints, including traces of calcium and titanium detected in its spectrum. Perhaps the most intriguing clue came from the cow's location. Unlike most supernovae, which occur inside star-forming galaxies, this flare erupted in a relatively quiet galaxy, a place where such violent events aren't expected. That odd setting hints that whatever triggered it might be even rarer than we thought, a once-in-a-century cosmic anomaly waiting to rewrite the textbooks. As astronomers continue studying the cow's aftermath, one thing is clear: this wasn't just another supernova. It was a glimpse into the universe's most extreme physics labs, where black holes are born, stars are ripped apart, and the rules we thought we knew get tossed out the window. And with new telescopes coming online, we might soon find more of these strange beasts, cosmic misfits that challenge everything we thought we understood about how stars die. Amid all the violent explosions and cataclysms we've explored, there's an invisible force operating on the grandest scale of all, one that doesn't destroy but disperses. Dark energy, the mysterious repulsive force permeating the cosmos, behaves unlike anything else in physics. Rather than blasting matter apart in a fiery burst, it stretches the very fabric of space between galaxies, accelerating the universe's expansion with a quiet, inexorable push. The numbers defy intuition. Since the universe's infancy, this enigmatic energy has grown from accounting for a negligible fraction of the cosmos's content to dominating over 70% of it today. The discovery of this accelerating expansion in 1998 came as a shock to astronomers studying distant supernovae. Instead of finding the universe's growth slowing down under gravity's pull, their measurements revealed galaxies racing apart faster over time, like dots on an inflating balloon, where each breath makes them flee from one another more rapidly. Subsequent observations confirmed this wasn't local behavior. Dark energy's influence appears uniform across the observable universe, woven into space itself. Some theories suggest it might be the cosmological constant Einstein once proposed, then discarded, representing the energy of empty space. Others speculated could be a dynamic field, changing strength over cosmic epochs. What makes dark energy so unsettling is its long-term consequences. While gamma-ray bursts and supernova obliterate stars, dark energy works on a more profound level. It prevents cosmic structures from forming in the first place. As space stretches faster, galaxies beyond our local group will eventually accelerate away faster than light can bridge the gap, vanishing from view as if swallowed by an endless horizon. Future civilizations born in those isolated islands would see only darkness beyond their galactic borders, their night skies devoid of external galaxies entirely. The most chilling implication: this process appears unstoppable. Unlike matter or radiation, dark energy's density doesn't dilute as the universe expands, meaning its repulsive influence grows stronger relative to everything else. In tens of billions of years, the distance between surviving galaxies will increase exponentially. isolating each like ships losing sight of one another in an ever-widening sea. Stars will still explode, black holes will still collide, but their light may never reach another observer again. Yet for all its strangeness, dark energy's existence helps solve one of cosmology's great puzzles: why the universe appears so finely balanced between expansion and collapse. Without this repulsive force, gravity would have long ago pulled everything back into a cosmic crunch. Instead, we live in a Goldilocks era where both forces create temporary islands of structure: galaxies, stars, planets amid the growing void. That we can observe and ponder such mysteries at all may be the ultimate cosmic irony. Our ability to study the universe's fate depends on our fleeting position in a brief window before dark energy erases all external evidence of it. When a star explodes, the blinding flash of light is just the tip of the cosmic iceberg. 99% of the energy actually escapes as ghostly particles called neutrinos, invisible to our eyes but carrying the true story of the cataclysm. These subatomic wraiths, so elusive they can pass through light years of lead without a single interaction, are the universe's silent witnesses to stellar death. Nowhere was this more dramatically illustrated than with supernova 1987A, the nearest observed supernova in modern history. On February 23, 1987, detectors buried deep underground, shielded from cosmic interference by Earth itself, suddenly registered a surge of neutrinos. 3 hours before the first visible light from the exploding star reached telescopes, these nearly massless particles had already raced across 160,000 light-years of space, slipping effortlessly through the outer layers of the dying star while visible photons remained trapped in the chaos. The numbers from that day still stagger physicists. Over just 13 seconds, neutrino observatories like Kamiok and in Japan and IMB in Ohio captured a total of 24 neutrinos, a seemingly tiny number, until you realize these detectors typically count just 1 or 2 neutrinos per day from all sources combined. Extrapolating from those precious few particles, scientists calculated the supernova must have released 10 to the 58 neutrinos total, more particles than there are grains of sand on every beach on Earth, all emitted in a single cosmic heartbeat. To put that energy in perspective, the neutrino burst alone carried enough power to outshine every star in the observable universe combined, if only we could see it. What makes neutrinos such perfect messengers from a supernova's core is their ability to escape unscathed where light cannot. When a massive star collapses, its core becomes so dense that even photons, normally the fastest things in the universe, are trapped, bouncing endlessly in the soup of free neutrons and protons. But neutrinos, with their vanishingly small chance of interacting with matter, fly straight out like bullets through fog, carrying pristine information about the explosion's inner workings. Their early arrival in 1987 wasn't a fluke. It was physics in action, proving that neutrinos truly are the universe's ultimate escape artists. The legacy of supernova 1987A's neutrino detection goes far beyond confirming theoretical models. It marked the birth of neutrino astronomy, proving these particles could be used to study cosmic events invisible to traditional telescopes. Modern detectors like IceCube at the South Pole now monitor the sky constantly, waiting for the next nearby supernova to paint a detailed picture of stellar collapse in real time. When the next one happens, whether in our galactic backyard or millions of light years away, those faint flashes in the darkness will once again tell the true story, hours before our eyes catch up to the universe's most violent spectacles. This invisible neutrino pulse isn't just a scientific curiosity. It's a lifeline for understanding how stars forge the elements that make up our world. The same nuclear reactions that produce neutrinos also create heavy atoms like oxygen, carbon, and iron, the building blocks of planets and life itself. By studying these ghostly particles, we're essentially reading the recipe for cosmic creation, written in a language older than light, And somewhere out there, right now, another star may be collapsing, its core flooding the universe with trillions of silent messengers waiting for our detectors to catch their whisper. Some stellar explosions don't follow the rules, they rewrite them entirely. Take V838 Monocerotes, a star that erupted in 2002 with a brilliance that briefly outshone our entire Milky Way, yet left astronomers scratching their heads. This wasn't a supernova, nor a nova, nor any known stellar outburst. Instead, it belonged to a rare class of cosmic events called luminous red nova explosions so peculiar they blur the line between stellar death and rebirth. The spectacle began when this unassuming star, located 20,000 light-years away in the constellation Monoceros, suddenly flared to over 1 million times its original brightness in a matter of days. But instead of fading quickly like a typical nova, it lingered for months, glowing an eerie red as its light echoed off surrounding dust clouds like a cosmic lighthouse. What made this event so baffling was what came next. As telescopes tracked V838 Mon's aftermath, they revealed something unprecedented. The star wasn't destroying itself, it was merging. The leading theory suggests this crimson flare marked the violent collision of two stars locked in a gravitational embrace. Picture two aging suns, their outer layers already swollen into red giants, spiraling closer over centuries until their surfaces finally touched. At that critical moment, their shared rotation whipped their atmospheres into a frenzy, ejecting vast shells of gas while their cores spiraled inward like water down a drain. The resulting explosion, part fireball, part stellar tango, created a shockwave that lit up the surrounding cosmos without fully obliterating the stars. Unlike supernova that leave behind black holes or neutron stars, luminous red nova like V838 Mon might instead forge a single, rejuvenated star from the wreckage, its chemical makeup scrambled by the merger's violence. The echoes from this event offered astronomers a 3D view of stellar destruction. As the initial flash of light traveled outward, it illuminated pre-existing dust shells the star had expelled in earlier, quieter epochs. Each concentric dust layer acted like a celestial movie screen, reflecting the explosion's light back to Earth with a time delay. By analyzing these light echoes, scientists reconstructed the star's history like detectives piecing together a crime scene, revealing that V838 Mon had been shedding material for decades before its final cataclysm. But the real surprise came when Hubble turned its eye toward the aftermath. Instead of finding a scattered debris field, the telescope captured a rapidly expanding nebula with intricate spiral structures, telltale signs of two stars entwined in a final dance. The merging stars had spun so fast they flung material outward in ornate patterns, creating a transient cosmic artwork visible for only a few brief years before fading into the darkness. This wasn't just an explosion, it was a stellar metamorphosis, proving that some stars don't die quietly or violently, but transform into something entirely new. Luminous red nova like V838 Mon challenge our understanding of stellar life cycles. They're cosmic reminders that the universe loves variety. Not every explosion fits neatly into textbooks, and sometimes the most dazzling light shows come from stars colliding rather than collapsing. As astronomers discover more of these events, each one peels back another layer of mystery, revealing how fluid and unpredictable stellar evolution can be. And somewhere out there, another pair of stars might be circling toward their own moment of fiery union, preparing to paint the cosmos with light that defies all expectations. At the heart of our galaxy lurks one of the most efficient engines of destruction ever discovered, a cosmic furnace where matter and antimatter collide in bursts of pure annihilation. Known as 1E 1740, 2942, this mysterious object nicknamed the Great Annihilator sits just a few hundred light-years from Sagittarius, a star, our Milky Way's central supermassive black hole. What sets this celestial monster apart isn't just its appetite, but its table manners. It's the only known source in our galaxy where scientists have directly observed streams of positrons, the antimatter counterparts to electrons, spiraling toward oblivion in a blaze of gamma rays. The scale of these collisions is almost poetic in its violence. When an electron meets a positron, they don't just disappear. They convert their entire mass into energy following Einstein's famous equation, erupting in gamma-ray photons with energies of precisely 511,000 electron volts. Now imagine this process scaled up to cosmic proportions. The Great Annihilator produces so many of these collisions that its gamma-ray output equals the energy of thousands of suns vaporized every second. It's as if nature built a particle accelerator the size of a solar system, where the fuel isn't gasoline or uranium, but the very fabric of reality itself. What makes 1E 1740, 2942 even more fascinating is its identity crisis. For decades, astronomers debated whether this object was a microquasar, a small-scale version of the supermassive black hole engines seen in distant galaxies, or something even stranger. Radio observations revealed twin jets of plasma stretching light years into space, typical of black holes feeding on surrounding material. Yet its X-ray emissions fluctuated wildly, suggesting unstable feeding patterns unlike anything seen elsewhere. The smoking gun came when gamma-ray telescopes detected the telltale signature of electron-positron annihilation, confirming this wasn't just another black hole. It was a cosmic matter-antimatter factory operating on an industrial scale. The origins of all this antimatter remain hotly debated. One theory suggests the Great Annihilator's black hole, likely weighing several times our Sun's mass, is stripping material from a companion star, creating a superheated accretion disk where conditions are so extreme that particle-antiparticle pairs spontaneously bubble into existence. Another idea posits that powerful magnetic fields near the event horizon act like cosmic particle colliders, accelerating electrons and positrons to near-light speeds before slamming them together. Whatever the mechanism, the result is the same: a relentless torrent of gamma rays pouring into space, each one a tombstone for a particle and its antiparticle that ceased to exist in a flash of pure energy. This antimatter inferno isn't just a curiosity, it's a Rosetta Stone for understanding some of the universe's deepest mysteries. The positrons detected here might explain a puzzling surplus of antimatter particles found throughout our galaxy, a riddle that's baffled scientists since the 1970s. Some even speculate that similar processes in the early universe could have tipped the balance between matter and antimatter, allowing our material cosmos to exist at all. And while the Great Annihilator's current outbursts are spectacular, they're likely just a preview. Models suggest it could become 1,000 times brighter if its feeding rate increases, offering astronomers an unprecedented lab to study matter's mirror image in action. So the next time you hear about antimatter in sci-fi as some rare, exotic substance, remember, our own galactic backyard hosts a natural antimatter cannon, where particles and antiparticles meet their end in a firework display that puts all human-made explosions to shame. And as telescopes grow more sensitive, we may soon uncover whether this cosmic oddity is unique, or just the first of many annihilation engines hidden in the darkness between the stars. Imagine a black hole untethered, invisible, and barreling through the galaxy at hundreds of kilometers per second, plunging straight through a star. This isn't some abstract nightmare scenario. Rogue black holes, cast adrift by galactic collisions or violent supernova, likely number in the millions across the Milky Way. One of these cosmic drifters passing through a stellar system wouldn't just disrupt orbits, it would unleash energy on a scale that makes supernova look like firecrackers. The moment of impact would be apocalyptic. As the black hole's gravity grips the star, tidal forces would stretch the stellar material into a blazing stream of plasma. Unlike a typical tidal disruption event where a star gets shredded near a supermassive black hole's event horizon, this collision would be far more chaotic. A hypervelocity smash-up where the black hole doesn't linger to feast but tears through the star like a bullet through water. The energy release would be twofold. First, from the star's catastrophic decompression as the black hole ruptures its core, then from the superheated debris crashing back together in its wake. For a sun-like star, the numbers are staggering. Even a modest rogue black hole, say 10 times Earth's mass, could transfer enough gravitational energy to vaporize the star in seconds, briefly outshining its entire host galaxy with a flash of X-rays and ultraviolet radiation. But the real fireworks would come from the gravitational waves. As the black hole plows through the star's dense core, the violent acceleration of matter would ripple space-time with waves detectable across the universe. LIGO and future observatories like LISA might catch this signature as a bizarre chirp, a sharp spike in gravitational wave frequency followed by a messy, prolonged echo as the star's remnants collapse inward. Now scale this up to a planetary encounter. Earth's fate would be both swift and eerily silent. A rogue black hole just 1 millimeter wide packing the moon's mass would pass through our planet like a ghost, leaving no initial crater. But its gravity would trigger earthquakes of unprecedented magnitude as it distorted Earth's interior, followed by explosive decompression of the mantle as the core collapsed hours later. The gravitational wave burst would be faint but distinctive, a single needle-like spike in detectors as the black hole exited the far side, carrying a whisper of our planet's destruction across the cosmos. The physics behind these collisions could rewrite our understanding of extreme gravity. Unlike mergers of binary black holes which produce clean, symmetric wave patterns, a rogue impact would generate chaotic harmonics, clues about the victim's density and composition encoded in the gravitational signal. These events might also solve mysteries like dark matter's nature. Some theories suggest primordial black holes could be hiding in plain sight, their presence betrayed only by rare, catastrophic encounters. While the odds of such an event in our cosmic neighborhood are vanishingly small, the universe is vast. Somewhere, right now, a wandering black hole might be threading the needle of a distant solar system, poised to rip a star apart in a flash of energy visible clear across the cosmos. And when it happens, the gravitational echoes will carry a reminder. In the darkness between the stars, the universe keeps its most violent architects. What if our entire universe is just one fragile bubble floating in an infinite cosmic foam, destined to pop at any moment? This unsettling idea isn't science fiction. It's a legitimate theory in physics called quantum bubble nucleation, and it suggests that the Big Bang might not have been a one-time event, but just the first domino to fall in an endless chain of universe-generating explosions. At the heart of this mind-bending concept lies the notion that the vacuum of space isn't truly empty or stable. Instead, it could exist in a false vacuum state, a precarious quantum configuration where the energy of empty space is temporarily trapped, like a marble balanced at the top of a hill, waiting for the slightest nudge to come crashing down. The staggering implication: if our vacuum is indeed false, a single quantum fluctuation could create a microscopic bubble of true vacuum, somewhere in space, a region where the fundamental laws of physics rewrite themselves to a lower, more stable energy state. This bubble would expand at the speed of light in all directions, its boundary wall a seething front of infinite energy. Every atom, every force, every law of physics we know would cease to exist in its wake, replaced by an entirely new cosmic order. From our perspective, it would be indistinguishable from instant annihilation. One moment the universe as we know it, the next an unfathomable new reality stretching outward at light speed, erasing existence as it goes. Here's where it gets even wilder. This process might have already happened before. The Big Bang itself could have been triggered by a false vacuum collapse in some parent universe, birthing our cosmos in a fireball of redefined physics. If true, we might be living inside one of countless cosmic bubbles, each with its own unique physical constants and laws. popping into existence across an unimaginably vast multiverse. Some theories even suggest these vacuum decays could explain dark energy, the mysterious force accelerating the universe's expansion. What we perceive as dark energy's gentle push might actually be the faint tension of our cosmic bubble's walls straining against the surrounding false vacuum. The most haunting part, we'd never see it coming. A true vacuum bubble could emerge anywhere, a light year away or at the edge of the observable universe, and we'd have zero warning before its boundary wall washed over us. There'd be no time to react, no chance to escape. The laws of physics themselves would rewrite in an instant, leaving no trace of the universe that was, like a dream dissolving upon waking. Yet paradoxically, this terrifying possibility offers a strange comfort, proof that the universe might still hold mysteries so profound they dwarf even our wildest imaginations. While the odds of such an event occurring in our cosmic neighborhood are vanishingly small, the implications ripple through modern physics. Particle accelerators like the Large Hadron Collider constantly probe high-energy states, searching for hints that our vacuum might be metastable. So far, the Higgs field appears stable, but the margin for error leaves room for spine-tingling possibilities. If confirmed, bubble nucleation would stand as the ultimate cosmic explosion, not just destroying matter but reality itself, while birthing new universes in its wake. Until then, it remains one of science's most electrifying what-ifs, a reminder that existence might be far stranger and far more fleeting than we dare to believe. In October 2022, astronomers tracking the cosmos stumbled upon something that defied every textbook on stellar explosions, a celestial object that just wouldn't quit. Nicknamed the Tasmanian Devil for its relentless energy, at 2022 TSD erupted not once but 14 times over several months, each flare packing the punch of a full supernova. This wasn't a dying star's final gasp. It was a cosmic encore no one saw coming, rewriting the rules of how stars explode. The first flare alone would have been extraordinary, a brilliant flash in a distant galaxy, initially mistaken for a typical supernova. But then it happened again and again. Like a cosmic strobe light, the Tasmanian Devil kept reigniting, blasting out energy in violent bursts separated by weeks or even days. Each eruption unleashed as much energy as our Sun produces in 30,000 years, yet the source somehow survived this self-destruction marathon. Telescopes scrambled to monitor the event, capturing X-rays, radio waves, and visible light that painted a picture of chaos. Most supernovae fade predictably after their initial explosion, their remnants glowing like embers in a dying fire. This object, it was a firecracker strapped to a dynamite factory, detonating in erratic, energetic fits. What could possibly fuel such a spectacle? Leading theories point to a newborn black hole or neutron star stuck in a feeding frenzy. Imagine a massive star collapsing under its own gravity, forming a compact object with an insatiable appetite. Instead of settling quietly, the black hole's magnetic fields might have channeled the infalling debris into a series of violent explosions, like a cosmic engine sputtering as it gulps down stellar material. Alternatively, the flares could stem from a magnetar, a neutron star with a magnetic field trillions of times stronger than Earth's, undergoing repeated starquakes as its crust cracks under unimaginable strain. The most baffling clue lies in the flares' timing. Unlike anything observed before, they followed no clear pattern. Some clustered within days, others spaced weeks apart. This irregularity suggests an engine far more complex than a simple collapsing star, possibly involving a debris-clogged accretion disk or a black hole jet processing like a wobbly top. Adding to the mystery, the flares weren't just energetic, they were fast, some lasting barely minutes. That's not enough time for shockwaves to propagate through a typical supernova remnant, implying the explosions originated in an incredibly compact region, perhaps near the surface of a neutron star or the event horizon of a black hole. The implications ripple far beyond this one event. If the Tasmanian Devil represents a new class of stellar explosion, there could be countless others lurking in archival data, previously dismissed as instrument glitches or oddities. Future surveys might reveal these repeating supernova as a missing link between ordinary stellar deaths and extreme events like gamma-ray bursts, and with each new detection, we'll inch closer to understanding how black holes and neutron stars, the universe's most efficient engines of destruction, can turn a star's demise into a fireworks show that refuses to end. For now, at 2022, TSD stands as a humbling reminder. Just when we think we've catalogued every way a star can die, the universe invents a new one. And somewhere out there, another cosmic Tasmanian Devil might be biding its time, waiting to light up the sky with its own defiant, unpredictable brilliance. After quadrillions of years, when the last stars have burned out and galaxies have dissolved into darkness, the universe will enter its final, silent chapter. But even then, the cosmos won't go quietly. Black holes, those last survivors of a once vibrant universe, will slowly evaporate in bursts of quantum fireworks. Thanks to Hawking radiation, these gravitational titans, some weighing billions of suns, will gradually leak particles into the void, their event horizons shrinking like ice cubes in a warm room. The larger the black hole, the slower its demise. A stellar mass black hole might vanish in a mere 10 to the 67 years, but the supermassive beasts anchoring galaxies could persist for 10 to the 100 years, a number so vast it dwarfs every timescale in cosmic history. Their final moments will be bizarrely spectacular. As a black hole nears evaporation, its temperature soars exponentially, culminating in a burst of high-energy gamma rays, a farewell flare brighter than a supernova, yet lasting just fractions of a second. Imagine a singularity the size of an atom, glowing white-hot with the energy of 1,000 nuclear bombs before popping out of existence entirely. This won't be a localized event. Across the cold, dark universe, black holes of all sizes will blink out one by one. Their death throws the last sparks of light in an otherwise featureless void. But even after the last black hole vanishes, the universe isn't quite done. In the unimaginable depths of time, somewhere beyond 10 to the 135 years, protons themselves, the building blocks of all matter, may begin decaying. If theories like grand unification hold true, these seemingly stable particles will spontaneously unravel, their quarks and gluons reassembling into lighter particles like positrons and neutrinos. Each decay will release a whisper of energy, barely a flicker compared to the fireworks of earlier epochs. Yet collectively, over eons, this process will dismantle every remaining atom in the cosmos: white dwarfs, neutron stars, even the cold, free-floating rubble of long-dead planets, until only a sea of subatomic particles and radiation remain. This isn't just the end of explosions, it's the end of structure itself. With no protons left, no new atoms can form, no stars will reignite, no planets will coalesce. The universe will be reduced to its simplest possible state, a thin, ever-cooling soup of leptons and photons, stretched infinitely thin by relentless expansion. Even the energy from proton decay will eventually redshift into oblivion, leaving nothing but absolute zero and darkness. Yet there's a haunting beauty in this fate. Every black hole's evaporation, every proton's quiet decay, carries echoes of the universe's fiery beginnings. The same quantum rules that birthed particles during the Big Bang will ultimately reclaim them, tying the cosmos's story into a symmetrical loop. From an incandescent origin to an icy, silent conclusion, the universe's final explosions will be less about destruction than transformation, a reminder that even in eternity, nothing truly ends. It just becomes something else. From the blinding fury of gamma-ray bursts to the eerie glow of antimatter annihilation, we've journeyed through 30 astonishing explosions that shape the cosmos. These aren't just celestial fireworks, they're the universe's architects, forging elements in their furnaces, sculpting galaxies with their shockwaves, and lighting up the darkness with bursts of raw energy. Every gold atom in your jewelry, every breath of oxygen you take, was forged in the heart of a dying star or the aftermath of a cataclysmic collision billions of years ago. These explosions don't just destroy, they create, seeding the cosmos with the building blocks of planets, life, and even the device you're using right now. Think about the scale of it all. Hypernovas unleash more energy in seconds than our Sun will in its entire lifetime. Magnetars crack like cosmic eggshells, sending starquakes rippling through spacetime. Black holes evaporate in bursts of quantum brilliance, while dark energy stretches the very fabric of reality itself. Each event is a thread in the grand tapestry of existence, proof that destruction and creation are two sides of the same cosmic coin. As Carl Sagan once said, we are made of star stuff. The calcium in your bones, the iron in your blood, the silicon in your phone, all of it was born in the hearts of stars and scattered across the universe by these unimaginable explosions. Every time you look up at the night sky, you're seeing the aftermath of cosmic violence that made your existence possible. The universe is far from quiet. Somewhere out there, right now, a star is collapsing, a black hole is merging, or a magnetar is cracking under its own magnetic strain. These explosions aren't just history, they're happening all around us, shaping the future of galaxies we'll never see. And with every new discovery, from gravitational waves to neutrino bursts, we're peeling back another layer of this cosmic drama. So stay curious. The next great cosmic explosion could happen any moment, and when it does, we'll be here to unravel its secrets. Hit subscribe to join us as we explore more mysteries of the universe, because the story of the cosmos is far from over, and the next chapter might be the most explosive yet. After all, you're not just watching the universe, you're part